Our first speaker in this session is Jinghao Zhao from University of California, Los Angeles. He's currently the first-year PhD student, and his research interests include mobile network system, mobile security, and mobile age applications. And today, he's going to present in person, finally, about their work on SEED, which is a SIM-based solution to 5G failures. Using that.
Okay, so hello everyone. I'm Jinghao Zhao from UCLA, and I'm glad to introduce our work, SEED, a SIM-based solution to 5G failures, to all of you. And this is a joint work with Zhao Weitan, Yifei Xu, Zhehui Zhang, and Professor Songwu Lu. So nowadays, as we know, the 5G has been widely deployed. However, the 5G failures has become the norm rather than exceptions. Our trace analysis finds that every 10 procedures of the control or data plan management signalings will meet one failure. And for all these failures, 73% of the control plan failures and 92% of the data plan failures will cause the disruptions longer than 10 seconds. However, comparing with the prevalent failures in 5G, the current handlings are pretty limited. So the current approaches for the failure handling take this blind retry approach. So first, let's see the modem, how it takes over the failures. First, when the modem faces failures, it will take this timer-based retry, which means when it sends out signaling to the base station, and however the failure happens, and then a timer will be brought up as the modem, and after several seconds, it will try to resend this signaling again and to see whether it can be successful or not. However, with this scheme, only 27% of the failures could be recovered within 10 seconds. And also, furthermore than the modem, the OS also takes some of the handlings. For example, the Android takes this layer-by-layer retries, and when the failure happens, it will first try to reset all the TCP connections, and if it still cannot work, it will try to re-register to the cellular network. And last, if it still cannot work, finally, it will try to restart the modem and try to see if the failure could be solved. However, the long intervals between these consecutive actions cause long disruptions. By default, 3.5 minutes was set as in the Android, so that if you go through the whole procedures, around you need nearly 10 minutes to recover at the hardware level. And also another type of solution is this application-based. So the application-based way, usually using this cross-source data from many UEs or user devices, so that you can know the network management, measurements, and also some failure cases. And then all these cases will be sent to the cloud server. So the cloud server cross-source data, do the analytics, and to figure out what's the potential reasons for this failure. However, the major issue for it is that when the failure happens, then the data plan has been broken. And basically, you cannot send any traffic from the device to the network or the reverse side. So with this one, as we can see, the network, although the servers potentially got some clues for the failure, however, it cannot notify the UEs about what has happened. And then the UE cannot get the instructions to perform the recovery. So to solve this issue, we propose the SIM-based failure diagnosis. We're leveraging the SIM card on widely applicable for all cellular devices and to do this failure handling. So first, the SIM card will infer the failures and also react for the corresponding recovery. And also, one feature is that our SEED enables the diagnosis without the data plan connectivity. Although the data plan has not been set up or has been broken due to the failure, our SEED could still get both sides of information. And last, the interfaces works on the commodity devices, and we do not need to change the mobile OS, modem firmware, or even base station. So two key questions. Let's first see the overviews of the SEED, how it proceeds this failure diagnosis. First, when failure happens, it will collect both sides of information from both the infra side and also device side. Then inside the failure, it will perform the diagnosis with the collected info and find out the root cause of this failure. And with this diagnosis results, we will trigger the corresponding reactions on the infra side or the device side. So with this solution, two key questions need to be answered by SID. First is that with limited capability of the SIM, for example, the processing, the storage, and how can the SIM card infer the failures and also do the reaction? And second, one dilemma this SID faced is that how to notify the failure cases upon the failures. Because when failure happens, actually, we cannot get some TCP or UDP connections between the device and the cloud. And how can we get the infra-side information for it? So before go to the details, let's first see some cases in 5G failures. So the 5G set up this connectivity with 3 stages, and the set up the control plane, data plane, and finally goes through data delivery. However, the failures could happen in every stage. For example, the most common failures in control plane management is this unsynchronized infra data status. So let's give a case. For example, this device connects to the base station 1, and then with this successful connection, it will set some internal status and also identities. However, due to the mobility, this device could move to another new base station. But the core side data is not synchronized in time, so that this internal data as the infra side is not synchronized with the device. And when the device tries to attach with some cache identities or status, then the failure happens. And also in the data plane, the most common failures comes from these outdated configurations. So these configurations could be embedded in the SIM card or the OS, and when the modem using this outdated configuration to try to attach. And then basically this outdated config cannot pass the checking at the infra side, so the infra will reject it, and then the failure happens. And without the updated config, the current approach like the modem retry or the OS retry cannot fix this issue and will make this long disruptions for applications. And also, for the data delivery stage, the port blocking issues and DNS failures are widely reported. Although you have successfully set up this control plane or data plane, and then basically the misconfigured firewall at the infra side could block some specific ports or traffic, and then the application, although you see that your mobile phones have the signal bars in the status successfully connected, however, it still cannot get from the application traffic. So with this one, as we can see, 4 different layers of data from the control plane, and data delivery, how can the SIM card get the information, knows that what's the exactly position of this failure happens. So the SID, leveraging this both sides of information from the infra side and application sides. From the infra side, it's leveraging the readily available 5G error codes. These error codes has been standardized and also deployed in this current 5G core. And also, from the device side, we leverage this, enable the interfaces with SIM card to let the application report the failures to the SIM. So when the failure happens, if it's caused by the controller data plane failures, then the network will send this error code to the SIM card as the diagnosis information. And also the application, it doesn't need OS to do the detection. When it detects the failures happens, it can directly report to the SIM with the corresponding information of its traffic, for example, port, IPs, or etc. With these informations, the SIM could perform this diagnosis with a simple decision tree leveraging all the collected info. First is that with this both sides informations, the SIM itself does not need to perform complex processing. For example, maintain complex state machines or the model checking. And also the second one is that with the readily available 5G error codes from the infra side, this solution could be fast and lightweight on both the infra side and also the device side. So with this information, and how can the SIM react to different types of failures? So the SID takes this multi-tier reset as the recovery scheme. So the multi-tier reset, let's give a simple example. For example, one time in this case, the failures happens in the control plane. And with the collected info from both sides, and the SIM could pinpoint the failure, said that this failure is caused by the outdated configurations. So I will directly reset this control plane. And then also at the same time, the network side could notify the SIM with the up-to-date config, and so that SIM could update the configurations as a device and only restart this control plane instead. And with this scheme, as we can see, Comparing with the timer-based retry or the layer-by-layer retry, we can directly pinpoint the failure's level and then do this direct reaction. And also, without the long intervals or long timers, we can do these fast recoveries with the SIM card. And all the interfaces, like these schemes to enable this recovery at reset the data plan or directly reset the control plan or reset the hardware, has been supported on the commodity devices. So we further designed the modes, 2 different modes to support the device with root or without root. More details you can refer our paper. So as we can see, leveraging the both sides info provides the benefits to the SIM card for the diagnosis. As the device side, the SIM could guard the application info and also control the modems for the recovery. And as the infra side, we can guard the misconfig corrections or guard the latest configurations. And also we can guard the 5G error codes from the lower layer as the diagnosis info. However, although the SIM card wants to leverage this information, one big question or dilemma the SID faced is that when the failure happens, and then the data plan has already been broken, and without this TCP or UDP connections, how can we guard that info? And second is that if we design some new signalings or some schemes to enable this communication between the device and the infra, potentially we will introduce new security risks, and highly possible that it's hard to fit into the 5G framework, which needs a long time to be standardized and also deployed by different entities, like the operators, device, and OS vendors. So with this one, the current SIM card actually supports this OTA channel, the over-the-air channel. However, this channel still relies on the data communication. Like you can send out some TCP or UDP traffic, but this cannot work when the failure happens. And what we do is that the SID leveraging the 5G signal links to embed the diagnosis information so that it could work under the broken data plan or even the data plan has not been set up. So let's see a case. For the downlink side, what we're using is the NAS authentication request. So in normal case, this authentication request is used to authenticate this UE, more like these devices. And the way is that the core side will generate the 16 bytes random bytes, and then this message will be sent to the base station and forward to the modem. And finally, modem will directly forward these 16 bytes to the SIM card. And then the authentication happens. What we do is that we replace these random bytes with the 5G error codes with a reserved prefix so that without changing the formats of this 5G signalings, and then it's transparent to the GNOB, the base station side, and also the modem side. And the modem could directly forward these error codes to our SIM card. And SIM card got the latest configurations, error codes, and so on. And with this one, the reverse side, what we use is this similarly for uplink. We embed the application failure reports that detect as a device side into the PDU session establishment request. So this request, without changing the formats, will also be transparently forwarded to the core side, and the core could parse it and guard the device side information to do the corresponding check-ins and also the configuration correction. So with this way, as we can see now, the SIM could guard both sides of informations, perform the data collection, the failure inference, and finally, most important, it could work under even without any data plan. We do not using any TCP or UDP traffic, and without setting up these whole procedures, during the failures, these signals could be still transmitted between the infra side and device side. So we evaluated with the SID on different scenarios, and then it can reduce the media disruptions by up to 792 times. And also we show the effectiveness with various applications. More details could be found in our paper. As for example, for the AR applications, it's potentially disruption sensitive, and we can reduce it by up to 270 times. So as a summary, the current blind and sequential retry approaches cause long disruptions and for the current 5G devices. And we propose this SIM-based failure diagnosis, which first provides the inference and reactions with the SIM card, and also it works under the failed data plan, and finally, it's compliant with the current 5G devices. We do not need to change the base stations, OS, or the modem firmwares, and could be readily deployable for the operators. So thank you, and I'm glad to take all the questions.
Hi, Simone Redhat in Karlstad University. Thanks for the presentation. I have 2 questions. So the numbers you presented about the failures are quite high to be actually acceptable by operators operating 5G. So you also mentioned that these failures are known and widely reported. So my question is, where they are widely reported, or where do we get to know them? And second, how did you rule out in your solution that the failures that you saw are not specifically related either to the hardware you're working on or either to a certain specific 5G network that you're testing your system?
Sure, yeah. Thanks for the question. That's a great question. So first, for the first one, the question is that how can we gauge this failure more like statistics or analytics? And what we do is that we collected these 5G traces with our UEs and with the 6 TB's public data set. So with that one, what we can see is that although the signaling procedures, for example, although the failure rate is high, but it's not so frequently performed on the 5G devices. For example, your phones will not periodically try to attach to the network. It will only happen when you restart your phone or you do some mobility cases. And then for that case, the handover, for example, these cases, then the failure is pretty frequent. And also all the more detailed analytics and also the failure types could be found in our paper. And for the second, how can we prove more like this public data set and also collect data set with our cases in real operators? We collected from these 3 major US operators and then shows the more like the prevalent failures. That's the first one. And also, how can we know that whether it's hard? The second question, if I understand you correctly, more like the major question is whether we can distinguish whether it's a hardware failure or it happens as a protocol stack. So the way is that, for example, when the protocol stack has some failures, actually more like using our schemes, the infra side could provide us a 5G error codes. If not any error codes, and also what the SIEM actually could do is that we have more details in the paper, but the SIEM could monitor the network performance or network modem connectivity conditions. So with that one, if the modems cannot respond to any commands, then potentially it's the failure caused by the hardwares, and that's out of our scope. So what we handle is the failures inside the 5G protocol stacks. And for some real hardware, like if you do not have any connection, any signals, or the hardware is completely broken, for sure, currently we will not handle it. Yeah. Any other questions?
Jun Kim from Princeton. Very good talk. I guess my question is more around so it seems you programmed the SIM and then the interface between the SIM and the mobile device. Is there a good open source tool so that people can just work on and program their own SIM, or did you use a proprietary tool, or did you make your own stuff? Are you making it open or things like that?
Yeah, so our SIM card applet has been open sourced. So we have previously published papers about it, and then it's based on the Java card, so that you can get a Java card like your more like bank card, and then just have the SIM size chip. And so you can program it with this Java card and install our SIM applet into it, and install it on the commodity phones, so that you can do all the tests and do further developments. Yeah.
Thank you.
Just a quick clarifying question. One of my concerns about this is the deployability, because it's not standardized. You could imagine that, say, one network operator could implement it first and other ones couldn't. So what happens if the SIM cards send these messages over the data, over the control plane using the NAS messages, and the core doesn't support that? Will there be an error, or will the core just ignore those messages?
Okay, yeah, that's a great question. So the key point of our paper is that, for example, in the normal deployments, and usually the SIM card, when you purchase, for example, the data plan from one operators, and then the operators will own the controls for the SIM card software and also the core side. So for sure, you cannot using some Verizon's like this operator SIM card to attach to the T-Mobile's network directly. And also you may potentially have some roaming or some contract. But usually what you do is that the operators could control the deployments of the SIM card software and the core side. So based on all the designs are more like focusing on this operator's angle so that all the softwares could be controlled. And also, actually, we provide some gradual procedure or deployment procedures so that you can deploy part of them and to support part of the failure handlings and incrementally to add more functions into the core and the SIM. Yeah.
Okay, let's thank the speaker.